Okay. We're starting right about now. Okay. It's going to be a Rust session. Let's see. I hope the audio is good. I mean, like, the music is not too loud. I can turn it down when we start. Meanwhile, we're just setting up my views. Right, let's go. Okay, I think we can start now. Come on, where is this? All right, so yeah, we're gonna again do Rustlings, and I think I need to yep. Okay. So you can tell me if the music is too loud, yeah? Well, we're gonna do Rustlings. We'll continue from where we left off. I think this is supposed to be... One second, let's try something. Okay. Yep. Turn down the music. Let's continue from where we left off. Again, Rustlings exercise, and then we're gonna be doing. I think we're gonna continue from traits, but I think there was something we wanted to look at in generics, I believe. I think it was in generics. Let's see. I know I wanted to. Was it there? No, it's no, I think we looked at the new type idiom, yes. Yeah, but I think we did not look at um the phantom type parameter. I think we didn't look at this. Um, anyway, we can look at that after now. There was something I wanted to look at in error handling. If was it in error handling now? Anyway, maybe we'll come across it later on. But I recall that on the Rustlings program that we were doing, I think it should be in. Yeah, so we should be looking at traits now. So let's go there. I'm gonna turn on music a bit. Hopefully it's okay. You can tell me. Yep. So yeah, we have actually we've actually looked at traits generally. Yeah. Yeah. I think we have. And we also looked at, yeah, I think this is what we wanted to see. Yep. So under validating references with lifetimes, we yep. I think this is where we left off. So let's continue. So if we wanted to, I think yesterday we saw the motivation for why we need to have lifetime annotations at all. Yeah. And we saw that when a given function returns a reference, the compiler is not able to know what that would refer to. It doesn't know for how long it should keep that reference because it refers to another memory location. So it doesn't know for how long will I keep this, especially like particularly if the reference depends on input parameters. So the question is going to be having is that for how long will I keep this? And it's the guarantee is that the return type, which is a reference now, the reference should not leave shorter than the reference that it refers to, right? So, yeah, I think we were seeing that with this example. So basically, the lifetime of the return type will be the shortest of the lifetime of the input. Yeah. Bitte. We also saw the syntax. And this is how it will look in the function signature. So you first have to declare the generic lifetime parameter inside angle brackets like this. And then use it. In this case, we're declaring a lifetime parameter, lifetime A. And then we're saying that both X and Y which are references, have the same lifetime, and the return um, reference also has the same lifetime. So I'm trying to express the following constraint. The return reference will be valid as long as both of the parameters are valid. Okay. I think there was something else we saw. Yeah. So what's happening here? Okay, so what's going on the relationship here? So for this one, I mean, we don't need a lifetime specification for this because this doesn't even vary. Like, let's see, you wouldn't need to specify a lifetime on the y parameter. Yeah, so there's no lifetime on the y parameter here because why would this be? So you just declare one lifetime parameter and then you give that to x, and you also say that the return reference is that one. Well, because inside of the function we only return the reference to just one of them, not the two input parameters. You don't need to keep track or bother about the other one. That makes sense. Yeah, because it doesn't have any relationship with the lifetime of x or the return value. All right, let's continue. Actually, 1 second. It says when returning a reference from a function, the lifetime parameter for the type needs to match the lifetime parameter for one of the parameters. Oh yeah, that's true, because this would be a dangling reference. This one here, so it doesn't allow this. This will not compile. Okay, that's fine. So ultimately, the lifetime syntax is about connecting the lifetimes of the various parameters and return values of functions. Okay. Yep. So now we go on to struct definitions. 1 second. I need to also send this. All right, let's do this. Yep. Okay, so struct definitions, how does it work? So for structs, yeah, we've been using own types before now, but now we want a struct to hold a reference, yeah? Or at least one reference. But you need to specify a lifetime. You need to add lifetime annotation on every reference in the struct's definition. Why is that necessary? It's a reference. The question will be, do I destroy the struct before, do I drop the struct before the reference or not? So it needs to be able to know that. I think that's the reason for that. So basically guarantees that the memory location that the reference points to would be the struct would not be dropped before that. Yep. Okay. I mean, this would be a lot easier if the compiler took care of this, to be honest. So you have a struct called important except that holds a string slice. Okay. And then you had to define the generic, the lifetime parameter. Yeah. Just the same way you define generic parameters here, and then you use it for specifying that here. And then what do? We say novel. We declare a variable novel and assign it to this string. We have a first sentence. Yeah, we just get the first sentence. That's it. And then we say we create an instance of the struct here. Part first sentence. Okay. So the struct has a single field part that holds a string slice, which is a reference. So yeah. So the annotation means that important except can't outlive the reference it holds in its part field. Yep. Wait, you're saying that the instance of important except cannot outlive the reference it holds in its part? What does that mean? I mean, I would imagine that you so if the instance is dropped, all right. I mean, this is just a reference. Part here is first sentence is, what does it give you? Split next, unwrap, and it gives you a string slice, or with I need to know what next and unwrap gives you. Do we have this? Oh, there was already a main there. That's fine. Okay. So you have it gives you an option that has a string slice. Yeah. So next gives you, when you unwrap it, yeah, you're gonna get this string slice, and that's what this is. So what happens when you drop this instance? Serious annotation means that an instance of important accept can't outlive the reference it holds. Well, let's read on and see. Yeah, novel is a variable that owns it. Yeah, the data in novel exists before the important accept is created. Yeah. In addition, novel doesn't go out of scope until after important accept goes out of scope. So the reference in the important accept instance is still valid. Yeah. I need to test this somehow, actually. Wait, how do we verify this thing that I think we can create like a scope. We have novel here. If I move first sentence here and yeah, and say we also move this. No. Okay. Not exactly. Okay. So obviously, that's I, or like the instance of important accept is only valid. I mean, it comes into scope here and goes out of scope here. But what about first sentence? Because this is a reference here. Right. I don't think what they say here is what they mean, because look, it says this annotation means that an instance of important accept can't outlive. Ah, yes, that's correct. I think I was reading it the other way around. Yeah, it's not possible for it to outlive the reference it holds in the part field. Yeah. So basically, what it means is that the moment first sentence, which is the reference, is dropped, this is dropped. Yeah, this is dropped. So How can I show that now? If we say if I decide to move first sentence, wait, what's this? Oh yeah, sorry, I'm struggling with this keyboard. It's sort of custom and sticking around it. Wait, right? I can do that, right? Do I have what options do I have actually? No, so well, whatever. I just do. Okay. Yeah, let's make this mutable. Yep. Temporary value dropped while borrowed. Yep. But I mean, this example doesn't really show why this is important, but we basically see that even though even when you use a reference as part of a struct, the struct itself cannot outlive the reference that it points to. That's just the summary of that. Yeah. Okay. So now we go to lifetime elision. Okay. So we've learned that every reference has a lifetime. And I need to specify lifetime parameters. So this doesn't have lifetime annotations specified. And the question is why? And that's because of lifetime elision rules. And there are a couple of them, so we need to see. It's talking about the reason why that code compiles been historical. Because previously every function needed explicit lifetime annotations. It would have looked like this. And what are the lifetime elision rules? So basically the rules allow us to not specify I mean they're baked into the compiler already, so we don't have to specify lifetime elision rules in certain cases. So the first rule is that the compiler assigns a lifetime parameter to each parameter that's a reference. So in this function, compiler will assign a lifetime. Well, so you can say it could create a lifetime parameter and assigns to this reference. A function with two parameters gets two separate lifetime parameters. So basically like this. Okay. So that's the first rule. The second rule is that if there's exactly one input lifetime parameter, it gets assigned to all output lifetime parameters. So in this case, we have exactly one input lifetime parameter. That's the one for the input x. It gets assigned to all output lifetime parameters. Yeah. The third one, if there are multiple input lifetime parameters, but one of them is self or, reference to self, a method reference to self, because that is a method, the lifetime of self is assigned to all output lifetime parameters. Okay. So let's look at these cases. So we have a function first word. It has an input parameter, s, which is a string slice. So automatically the compiler would create a lifetime parameter, and then so the first rule is that every input parameter gets a lifetime. Yeah, every input parameter as a reference gets a lifetime parameter. So one will be created and given to this. Yeah. And the second rule is that if you have exactly one input lifetime parameter, it gets assigned to all output parameters. Okay. That's why this can be deleted because of 1 and 2. So it would. So the compiler applies the first rule. Each parameter gets its own lifetime. So you call it lifetime A, and then it will look like this when that pass happens. For the second rule, exactly one input lifetime. Yeah, then it gets assigned to all output, and then you'd have this. Yeah. So if we look at this example as well, this one here, it also did not have a lifetime. Do you have any lifetime annotations on it? So let's see what the compiler will do. First rule, all input parameters get its own lifetime. Every input parameter gets its own lifetime. So lifetime A, for example, and then, but if we go by that, then it means you would have A and B, for example. Yeah. And then X would get lifetime A and Y would get lifetime B. And then by second rule, second rule would not apply here. Because you don't have exactly one input lifetime parameter. Third rule also doesn't apply. So basically you would be left with something that looks like so you would create the lifetime parameter. Actually, we need two of them. Wait, let's write the function itself first. So you have a longest that has x, which is a string slice, and y, which is a string slice, and it gives you a string slice. Yep. And let's just say it returns x, right? Interesting. Why do you need to have missing lifetime specified for this function returns a borrowed value. I mean, based on what we saw earlier, why does this even need you to specify the lifetimes? Because, yes, yeah, I recall why. My point is that the function itself returns a reference that it only depends on one, not the two of them. But anyway, you still need to do that because the compiler needs to know for how long that reference should be valid for. So look at what I mean. So let's say you have okay. These are two strings. And then you say let result be actually let result be longest. Yeah. So why that's needed? I mean, why you need the lifetime annotation for this is that by the time you pass the reference, by the time we pass the references to these memory locations to this function, you pass control here, the compiler needs to know, it needs to be guided as to for how long should I keep these variables, for how long should I keep them? And I cannot drop, it is to guarantee that I cannot drop the reference. I cannot drop the reference as long as this is, as long as this variable is valid. So you need to keep that. So you need to point that to add to it explicitly. That's why that's necessary. Yep. Anyway, that's the reason. But for here, we would need to declare a lifetime parameter. And again, because the function itself only depends on one of the input, not the two of them, we can just specify that for the one. And that'll be fine because it doesn't depend on y here. Yeah. But anyway, we were looking at lifetime addition rules. And I think that doesn't even apply here actually, because yeah, for longest, I think what would generally happen for lifetime addition rules here is that you would have because we said every input parameter gets a lifetime, right? then you'd have like but actually in this particular case we just give the both of them the same, and then we don't need this one. So whether or not we say um, whether or not we say that, that'll be fine. But anyway, let's proceed. Yeah, but this is what we would have gotten. Yeah, but okay. So second rule would leave us with this, but there's no lifetime annotation on the return reference. So second rule doesn't apply because there's more than one input lifetime. Yes. Third rule doesn't apply as well. So none of the parameters are self, and this is why we need to specify it. Yep. Okay. So we get an error when we try to compile because the compiler worked through the lifetime addition rules, but it still couldn't figure it out. Yep. Okay, that's fine. Let's go to method definitions. So they're declared after the implementation keyword, just like generic parameters. And then you use them. They're used after the struct name because they're part of the struct type. So, like so. So, okay, so in method signatures inside the implementation block, references might be tied to the lifetime of references in the struct field, or they might be independent. In addition, the lifetime addition rules often make it so that lifetime additions are necessary in method signatures. So let's see the example. So this is the implementation. We have a method named level, and it takes a reference to self. And remember the third lifetime addition rule that if we have an input parameter that is reference to self, then the output gets the same lifetime. So basically it's elided. You don't need to do that. Which is not a reference to anything. Actually, the return doesn't refer to anything. So if this was referring to if it was a reference, then I guess let's see, lifetime parameter declaration. So we're not required to annotate the lifetime of the reference to self. What do you mean? Because of the first lifetime addition rule. The first rule is that every input gets its own lifetime its own lifetime, yeah, parameter. Okay, so let's say that got deleted. Hold on, wait. Let's back up a little. So even though the return is not a reference, you still the lifetime edition rules still count. I mean, the compiler is still going to treat it like that. What do we have for important except part? Okay. But this sounds to me, this should read that because of the third lifetime edition rule, not the first, we're not required to annotate the lifetime of the reference to self. Okay, yeah, that's the first one. That's correct. Yeah, that's correct. Okay, so here's an example where the third lifetime edition rule applies. But yeah, in this case, we have the output is a reference. Yeah, so this makes sense. Okay, so again, first rule, every input gets its own lifetime. In this case, you would have lifetime A and B, for example. This gets one, this gets one. And then based on the second rule doesn't apply because you don't have exactly one input, but the third one applies because you have a reference to self and the output gets that lifetime. So that's why they are all edited here. So what I mean is this. Announce and return, right? Self announce. I mean this. So because it's just like generics, yeah. Just call it announce, and then it takes reference self, right? And then so right, so that's the announce, and I think what was it doing? It was okay, it's working. We can do like a format. Yep. Can return cannot return value referencing memory. Cannot return value referencing temporary value. Returns the value referencing. Oh, so Um, yeah, I think this would create a variable inside of here and to lead to a dangling reference we're trying to avoid. Yeah. So how did they do this here? Let's see. Oh yeah, so it's returning the. Oh yeah, because we already have self actually. We can just even use that one, right? Um, okay. So if we were to go with the lifetime addition rules, it would be like this, yeah. So we would have lifetime A and lifetime B, yeah, and this would get lifetime A, and this would get lifetime of lifetime B, and this all have what we get after the first rule gets evaluated, and then it says what lifetime name A shadows a lifetime that's already in scope lifetime A. Wait. So how does it work when you have methods? When you when you have, okay, wait, you already declare the lifetime, um, wait, I need to ask this question, to Claude. Where's Claude? Okay. For how do I call it now? For lifetime rules in Rust, um, so I have this. Lifetime addition rule one would mean that two lifetime parameters get created in a nouns. what happens to lifetime A? The lifetime is already declared and tied to self. So when the iteration runs on the method signature, it doesn't ignore lifetime A. It sees that self already has a lifetime A from the implementation block. Hmm. So rule one, for each elided lifetime in an input position gets its own distinct lifetime parameter. Yes. So applied to this, yes. Self get lifetime A, not a fresh one. So it inherits the one from the implementation block. Okay. Because self is this already has lifetime A baked in. Announcement gets a fresh lifetime, say lifetime B. Okay, so that's it. Right. Okay, that makes sense. Okay, so again, so taking that what we know about it, we already have a lifetime annotation, of course, yes, created here. So that means because each gets its own, so we can have something like this. Wait. Okay. So by the time the first row runs, we have this, or at least something like this, and it's already telling us that explicit lifetimes can be elided, yeah, because the lifetime run takes care of it. And by the time the second row runs, which is that if you have exactly one input, the output gets that. Second row doesn't apply because we have two input parameters, but we have the third rule, which says that if you have reference to self, oh wait, sorry, it's supposed to look like this actually. Yeah. So you have reference to self, then the output parameter gets that lifetime. And that's it. Okay. So actually you can just say this, right? Oh, no. Because they don't have the same names. Okay, that's correct. Yeah. So this would mean that lifetime of result becomes the lifetime of val, or rather the reference to val here. So result, which is an instance of important except, is valid. Yeah. Yeah, you cannot destroy this or drop this. Um, so basically, result has to stay in scope, or rather, um, val has to, or a result cannot be shorter than val. That's it. That's just the best way to say it. Yep. Okay, it's basically the same thing as the other one. As with regular lifetimes, even when you're dealing with structs and methods. Yeah. So now static lifetime. This is a special case. That the affected reference can leave for the entire duration of the program. All string literals have the static lifetime. Mm-hmm. So I guess they're also elided then. So if I say okay. Okay. You might see suggestions in error messages to use a static lifetime, but before specifying static as the lifetime for a reference, think about whether or not the reference you have actually lives for the entire lifetime of your program, and whether you want it to. Most of the time, an error suggesting static lifetime results from attempting to create a dangling reference. Okay, or a mismatch of the available lifetimes. So tries to fix the problem. Not specified lifetime. Okay, so what? Okay, so using them in generic type parameters. Okay. So you have a generic function, and then you have a lifetime parameter here that's created, and it's assigned or is given for x and y here. So basically, the inputs x and y and the results all have the same lifetime. Okay. Longest function returns the longer of two slices. Has an extra parameter named an, which is a generic type. This an here is just, it's not used. It's just used with trade bounds here. Can be filled by any type that implements display trait. This extra parameter will be printed using. Oh yeah, we printed here. I didn't see that before. Okay, we printed using that. Because lifetimes are a type of generic, the declarations of the lifetime parameter, lifetime A, the generic, they go in the same list inside angle brackets. You mean this? That's fine. Okay. I think that's it for this chapter here. So if we go back here, additional common traits, talking about clone, display, debug. But anyway, let's try to solve some of this here. So it says the trait append bar. It has only one function, which appends bar to any object. Okay. Sorry, 1 second. Okay, we're back. So the trait append bar has only one function, which appends bar to any object implementing this trait. This is it here. Real function is this is the trait, but it's not implemented. There's no default implementation. That's my point. There is an implementation for string. Yeah. And then we should implement append bar for the type string. So what we do here is to say append bar so it will take string anyway. Yeah, so it returns a string, so it will be, we can do format, yeah, and wait, actually it just appends bar. The easiest way to do this is self.bar. That's it, right? Why not? Yep. And we have full append bar, and this is on string, so we're implementing our own trait on a core. Wait. Yeah. I call struct. Nice. I want this thing. Come on, check. I think this thing is not working. Yep. So that one passed, so we can do the second one. So the trait append bar defines an item append bar. Oh no, this is not what we should be reading. We should implement the trait append bar. We should implement the trait append bar for a vector of strings. Append bar should push the string bar into the vector. Append the trait append bar for a vector of strings. So we should implement append bar for a vector of strings. Well, first of all, our trait is not generic, so that's fine. For vector strings. Okay, yep. And we should push the string bar to the vector. So it will be self dot push. Yeah, for pushing an item to the vector. Bar. No. Wait, when you push this, you have to return yeah, this is not a string, right? Yeah, this is a string. Do you have any function that we can yeah, it's a string, yep. Can call to string on this. Easier, right? Yeah, you cannot mutate the variable. Implement the trait append bar for a vector of strings. Append bar should push the string bar into the vector. Well, self. Is it possible for us to do? Would that not change the signature? No, it doesn't, because we're actually creating one here. Okay. So we have a mutable variable, We create the vector on this side. We create foo, and then we call the append bar on it, and we are certain that by the time you unwrap the you will get bar, and then again you get foo. Wait, what? Oh yeah, these are vector strings. This is now it's a vector strings. Okay, append bar. Yep, I think it's what we want. So these I want to confirm. Look, and we can't print this, right? Because it's, well, we can actually. Yep. Yeah, because it moves, right? It moves to append bar. So by the time you move it, you can, this value is dropped. Value is dropped here. So you don't, yeah, okay. Okay, that's what if I say, I mean, I wanted to show that this, it's the variable that would actually mutated, but anyway, it's dropped, so that's fine. So there's no need to run this video because we have what chapter is it even? Straight what? 2? Yep. Okay, so the next one. What's wrong? Let's restart this keyboard. Give me a second. Turn into life issues. Here. Okay, so what did we do here? Okay, we wanted to look at the next one, right? Third one. Yep. So we have a trait called licensed. We should add a default implementation for licensing info so that implementers like the two structs below, this and this, can share the default behavior without replacing the function. The default license information should be the string default license. So we have licensing info, and we should add a default implementation for licensing info. It's a string and it should return what it should say. Okay. And these two should get it. So because licensed is implemented for some software and for other software, then you can call licensing info on instances of some info and other info, and it will work. So basically, have licensing info is default license. Yeah, some software you're creating one, some software, an instance of some software, an instance of other software, and you're doing the assertion here. Yep, that's fine. Next, trait 4. I'm not sure what's wrong with. Right. Okay. And now we have licensed again. We have a licensing info. This is the trait. Okay, yeah, this is the default implementation. And we should fix the compiler error by only changing the signature of this function. So what is it? What do we have here? We have a function called compare license info, software 1 and software 2. Oh yeah, they're both trying to compare the licensing info for the both of them. So this should be the wait. This should be licensed. This should also be licensed. Yeah. What's wrong? What's the expected one of these is a bool. So what's wrong with this? Found that. Oh wait. think expected type found the trait. Oh wait, expected type found the trait. I think I know what you want. I think you want this to be that it's an implementation of licensed. Yeah. And an implementation of licensed. There's another way that we can do this actually. We can. Hey, I see his Boix. How's it going? It was a cool session you had yesterday. Yeah, I liked what you were showing as well. Yeah, yeah, it's going good. Yeah, I'm wrapping up the trait exercises for Rustlings. I was gonna say that for this one, there's another way that this can be written without the implementation keyword. I think is we can create a generic type here, and I think we can say software one. I think we can say this, right? And it implements licensed. Yep. Right? Is this correct? Let's see. Why do we have expected some software, found other software? Why? Okay, so let's see what we have. We should fix compiler only by changing the signature of the function. Well, that's what they wanted us to do. We did it, but I was just checking what else is possible for us to do here. But why is the... So we have some software, other software, and they both implement licensed. So why do we have this compare license types? Saying that it expects some software and found other software. Doesn't make sense to me, right? Or is it because we introduce a single type? Right. Maybe that's why. Let's see. Okay. Oh yeah, I think that's why. Yeah. So. Can we do it like this? No. How? Ah, wait. It's like T. It's not. Let's do it like. I mean, this is repetitive to be honest, but Yeah. Okay, we can also do this. It works. Okay, so 5. I notice this thing breaks when I when I switch, but yeah. Okay, so we have some trait. We have some function, which is a method of the traits. Yeah. And then we have other trait. Okay. Also returning a bool. We have a struct, a unit struct here. We also have, we implement some trait for some struct, another trait for some struct, right? And then same thing we do for, okay. Yeah, same thing for other struct. So we should fix compiler error by only changing the signature of this function. So we have some functions which takes an item of a given type, compares some function on item with other function on item. So some function and other function. So so basically item has other function and some function. So basically item is item has the behavior both for other function and some function. So the item is some trait and other trait. Okay. So what will this one be? For it to have the both of them, it cannot be some trait anyway, because some trait doesn't have other trait. You have some struct. You implement some trait for it, for some struct. Oh yeah, so, but you also have other struct. Item needs to implement both traits. Yes. Yeah, exactly. Item needs to implement both traits. Some struct implement both traits. Other struct also implements both the traits. So, well, let's do this then. Let's see some struct. Okay, so let's see the test. I said some func, some struct, some func, other struct. Yeah, that's the other part now. So there's also needs to be and you want us to just change this type here. I mean, I don't see. I guess we can. I guess there's one way to do this is to say it's an implementation of some trait plus other trait. Yeah. Yeah, okay. This is correct. This is the correct way to do it. However, the other way to do it, I think like we were saying earlier, was to do. We introduce a generic parameter, type parameter here, and we can say that, yeah, we can say that item is, oh, sorry. We can say that item is, okay, now I'm typing a lot of um, things. Yeah, so we can say that item, well, first we introduce a generic type parameter, and then we can say that item is that generic type parameter, and then we introduce a where clause where the generic type parameter implements some trait plus other trait. Yep. Okay. I think we're done with that. The next is a quiz, actually. It's a quiz. So I think I'm done with this for today. We'll probably continue tomorrow. I see, I guess, Boix. I don't know if you're still there, but I wanted to show you. So I had this other program from before. I can show you. Um, so I think I was doing, what is it actually? I don't, is it? I think I had this, yeah, let's see. No. Yep. So I was doing, so I was using an enum for the errors. I wanted to use anyhow error then, but I said no. I mean, I wanted to really write the errors, the error types, and handle them because I was getting into it to try to master the way it worked, and then I think I had like oh yeah. So see, so basically everything was my type. That's the generic thing that was returned. And I think I had, where's that even? Where's lib? So we have something like, is it this I want to show you actually? And probably. So when I was watching your stream yesterday, I I will be coming back here pretty soon because it gave me some inspiration around what to do with this thing. Yeah. But anyway, that's it. Then see you tomorrow, I guess. Yeah. All right. Ciao.